Okay, so today we're going to be starting the notes for our next unit. The name of this unit is called Waves and Optics. And remember, you can always access these PowerPoint notes on Canvas under the appropriate module. Okay, so this unit is, again, talking about different types of waves and optics, and there's a lot to it. There's not a lot of equations in this unit. But a lot of the stuff we're going to be talking about is conceptual and kind of definition and concept-based questions. We're going to be talking about different types of waves, their properties and behaviors, and then some applications of waves, particularly with sound and light and the electromagnetic spectrum. So again, there's a lot of information in this unit. It is quite a long unit. Now the good thing is, like I said, there's not a lot of calculations. There's not a lot of equations that you have to know and use, but it does have a lot of details that you just need to remember. So make sure that you're taking good notes. Again, remember you can access these PowerPoint notes through the appropriate module in Canvas. So please feel free to refer to them, and I would encourage you to take notes on your own using a notebook or Google document. So this is slide 5. We're going to go on to slide 6 and talk about the nature of waves. Okay, so the first thing, since this whole unit is about waves, is to answer the question, what is a wave? And so in the notes it says, a wave is a repeating disturbance or movement that transfers energy, but not matter, through space. And if you read that again to yourself, a repeating disturbance or movement that transfers energy, but not matter, through matter or space. Okay, think about some examples of waves that you might know about. Okay, so just to name a couple off the top of my head, we have water waves, we have light waves, we have sound waves, and those are just some of the basic types. Now you might ask, like, what about radio waves or microwaves? Those kind of fall under light. Light is what's called an electromagnetic wave. And so those would fit under that umbrella. You also have, like, seismic waves with earthquakes. If you've ever gone to like a football game or a baseball game, you might have seen the crowd wave where people in the stands stand up and stand down, and it creates kind of a wavy effect. That's an example of a wave. Okay, so there's probably lots of waves that you could come up with if you had enough time to think. I would encourage you to watch this video in this PowerPoint slide. Check that out. On the next slide, it kind of repeats this thing again. It says waves transfer energy, but not matter. And so the example I want you to see here is here is an example of a pebble that's been thrown into a pond, and you can see the ripple pattern that's being made. That is a water wave. Okay, now what's happening is as the wave travels outward from where the pebble's dropped, it makes the water spread out, or at least appear to spread out. If you actually were to put, let's say, like a little floating device or like a flower that's fallen in the water and you watch it, it's actually not going to move out from where the pebble is. It's only going to move up and down. And again, I would encourage you to watch the video in the last slide so you can see that. But the idea is, even though there's the appearance that the wave is pushing things out from the center, that's not actually happening. Okay, because waves transfer energy, but they don't actually transfer matter. And so it's not that the water itself is spreading out. It's because the water itself is just moving up and down. It's the energy that's traveling outward in kind of that circular motion. Okay, so it's important that you understand that waves transfer energy, but not matter. Okay, and so we're going to talk about mechanical waves. Okay, particularly transverse and longitudinal waves. And so this is just kind of some definition-y things that you would want to add to your notes. It says a mechanical wave are waves which require a medium. Now, you might ask, what is a medium? That's a word we're going to be using a lot. Okay, so a medium is a form of matter through which the waves travel. So basically, a medium is whatever the wave is traveling through. So for example, as I talk and you listen to my voice, the medium is probably the air. Okay, now it doesn't have to be the air. You can hear sound underwater. If you put your head underwater and yell to your friend in the swimming pool, they might be able to hear you. In that case, the medium would be the water. Okay, or if you imagine, like, seeing through your glasses, light is traveling through your glasses, and as it travels through your glasses so you can see, that medium would be glass. If you look at somebody through a window, then as the light travels through the window, the medium is glass, and then it travels out of the window and it goes through the air, which is another medium. And so a medium is just whatever the wave is traveling through. Now, some types of waves, electromagnetic waves, actually don't require a medium to travel through. Okay, so light, X-rays, infrared, ultraviolet, microwaves, radio waves, all of those things are types of electromagnetic waves that actually don't require a medium. They can travel through a medium, but they don't require one. Most waves don't have that property. Okay, so most waves are what's called mechanical waves. And again, a mechanical wave is a wave which does require a medium. Okay, so in other words, you have mechanical waves which do require a medium, and electromagnetic waves which don't require a medium. Okay, now that's one way to classify waves, is into either mechanical, or electromagnetic. Okay, but there's another way to classify waves that we're going to talk about, and that's into either that's the electromagnetic. It ran off the page, sorry. Electromagnetic. You can classify waves as either transverse or longitudinal, and so that's what we're going to do now. I'm going to erase what's on this slide. Okay, so you've got some different types of waves, or different ways to classify waves, I should say. And so the first one we're going to talk about is what's called a transverse wave. Okay, a transverse wave, if you ask somebody to draw a wave, they would probably draw a transverse wave. Transverse waves are typically what people think of when they think of waves. In a transverse wave, you can read what the definition says. In a transverse wave, the matter in the wave moves up and down perpendicular, or in other words, at a right angle to the direction of the wave. If you don't know what perpendicular means, that just means that whichever way the wave is moving is at a 90-degree angle to the direction that the particles are moving. So for example, you can see in this animation here, the red thing moving up and down is generating the wave, and then each of these black particles in the wave is also going up and down. However, the wave itself is going to the right. Okay, so in other words, the particles are going like this, up and down. That's what the particles are doing. But the wave is traveling to the right. Now, if the particles are moving up and down and the wave is traveling to the right, let me draw that together. Okay, this is the direction of the particles, up and down. The wave is traveling to the right. There is a 90-degree angle right here, and therefore this is a transverse wave. Okay, that's why it says perpendicular in the definition. Okay, the matter in the wave moves up and down perpendicular or at a right angle to the direction of the wave. So you can always figure out what type of wave it is by figuring out which way are the particles moving, which way is a wave moving, and thinking, is that perpendicular or not? Okay, in a transverse wave, they should be perpendicular. And again, transverse waves are the most common types of waves. That's why if you ask somebody to draw a transverse wave, if you ask somebody to just draw any wave, they would probably draw a transverse wave, because most waves that you experience on a day-to-day basis are in fact transverse waves. Okay, so I'm going to erase this. Okay, but there's another type of wave, and this is called a longitudinal wave. Okay, now the difference between a longitudinal wave and a transverse wave is in a longitudinal wave, the matter in the wave moves back and forth parallel to the direction of the wave. Okay, these are also called compression waves, but it's more common to call them longitudinal waves. And you can see in the animation how this works. If you look at the red dots in the animation, you can see the red dots are moving left to right and then back again. Okay, so the red dots, or all of the dots actually, are moving like this. Now, if you ask which way, in other words, this is what the particles are doing in the wave. Now, if you ask the question, which way is the wave moving, you can see this black arrow is showing you that the wave is actually moving to the right. Okay. Okay, so the particles are moving back and forth. The wave is moving this way. Okay, notice that's not a 90-degree angle. That is actually a a 0-degree angle or 180-degree angle. In other words, the direction that the particles are moving and the direction that the wave is moving, this is the direction that the wave is moving, are parallel. Okay, and so that is characteristic of a longitudinal wave. Now, there are some examples of longitudinal waves that we're going to talk about. Again, the vast majority of waves are actually transverse waves, but you still need to know the difference between the two. Okay, so just to go to the next slide. This slide, I don't think there is any new information. There are some videos I would definitely highly encourage you to check out. Again, you have access to this PowerPoint on Canvas, or you can just type in these URLs right here. I would highly recommend that you check those videos out, or just go to YouTube and Google or search like transverse versus longitudinal waves so you can see the real life differences between the two. Okay, again, this is like a slinky or a really long spring, and you can actually use a slinky to make either transverse waves or longitudinal waves, either by moving your hand up and down or pushing the spring in and out like this. This would be for a transverse wave, and this would be for a longitudinal wave. And this slide is just showing you an animation of each one. Obviously, the one on the top is an example of a longitudinal wave, and the one on the bottom is an example of a transverse wave. Okay, so and then this slide just kind of gives some examples. If you want to pause it here and add these to your notes, that's fine. It's basically just a repeat of the definitions and some examples of each one. Now, I do want to point out the fact that there's way more examples of transverse waves than longitudinal waves. The most common type of longitudinal wave that you might see is a sound wave. All sound waves are longitudinal waves. So anytime you hear sound, whether it's talking or singing or playing any type of musical instrument, that is creating a longitudinal wave. Okay, typically in the air, but it could happen in other types of media. Now, the list of examples for transverse waves is much more extensive because the vast majority of waves are actually transverse waves, water waves, waves on a string, the wave that crowds do at sporting events. If you've ever seen somebody do the wave, or not a single person, but if you've ever seen a crowd do the wave, like a football game or something, the individual people stand up and down where the wave is moving to the left or to the right, right? That's at a perpendicular 90-degree angle. So that is an example of a transverse wave. All types of electromagnetic waves are transverse waves. Light, microwave, radio waves, infrared, ultraviolet, X-rays. Those are all transverse waves. Water waves, if you think like throwing the pebble in the pond and it makes a ripple, that is creating a transverse wave because the water itself is going up and down, but the wave is spreading out away from where the pebble was dropped. And waves on a string, that's basically, you can think like any string instrument is creating a transverse wave. Yeah, so the most common example of a longitudinal wave is definitely sound wave. Now, you do definitely need to know the different parts of the two types of waves, especially the transverse wave, just because that's the most common one. The top of each transverse wave is called the crest. The bottom is called the trough. The middle line here, this dotted line, this is called the rest position. Okay, and then we have something very important that's called the wavelength. Okay, make sure that you know what wavelength is because you're going to be using it a lot and referring back to it a lot. The wavelength is the distance on a wave from one point on the wave to the next corresponding adjacent point. Now what that means is you pick a point on the wave, any point on the wave, and you measure horizontally until that point repeats itself. So for example, from here to here, that space is a wavelength. Okay? It is the length of the wave. Or you can measure from the top of one crest to the top of the next crest. Or you can measure from the bottom of a trough to the next trough. It doesn't matter. As long as you start at one point on the wave and you keep going until you reach the next corresponding point, that is one wavelength. Okay, now if you look at the name wavelength, you might think it's measured in units of length, and it is. So typically you see wavelength in like inches or centimeters, probably meters because that's the SI unit for length that we use. Okay, but wavelength is something you're going to see a lot. Now, while I'm at it, I will also tell you that the symbol for wavelength is this. Okay, this is the Greek letter lambda. Okay, it looks like an upside down Y, but that is the symbol for wavelength. Okay, so when you see a lambda in any equation, that stands for wavelength. Okay, I'm going to go to the next slide. Pause it here if you need to. Okay, now, even though longitudinal waves are not as common, you do sometimes see them. Longitudinal waves don't have compressions, they don't have crests and troughs, but they do have wavelengths. It's defined in the same way, the length from one point on the wave to the next corresponding point. Instead of crests and troughs on a longitudinal wave, you actually have compressions and refractions. And so the compression on a wave, if you look right here, or let's say right here, the spot where the wave kind of bunches up the most, that's called a compression. And the space in the middle here where the wave spreads out the most, that's called a refraction. Okay, so instead of having crests and troughs, you have compressions and refractions. Right? Instead of having crests, you have compressions. Instead of having troughs, you have refractions. But the wavelength is still defined the same. So you can measure the wavelength from like one compression to the next compression, or from one refraction to the next refraction. It doesn't matter. Okay, wavelength is still the same either for either type of wave. Okay, and then finally we're going to talk about frequency. And so we've already talked about wavelength. Do read what it says here. As far as the units go, wavelength is measured in things like, meters, centimeters, millimeters, inches, feet, I guess you could. Typically, most often, you're going to see wavelength measured in meters, right? We've seen meters before. But there's also something called frequency. Okay, and frequency, the definition is right here. I would highly encourage you to add that to your notes. It is the number of waves that pass through a point in 1 second. Okay, that is the definition of frequency. Now, the symbol for frequency is a lowercase f, just like the symbol for wavelength is a lambda that looks like an upside down Y. Now, wavelength is measured in meters. Frequency is measured in hertz. Okay, so 1 wave per second is 1 hertz. So if I write down f equals 2, I don't write out the word hertz, I write Hz. So 2 hertz means that 2 waves is passing through 1 point per second. Okay, now wavelength and frequency are inversely related to each other. In other words, if you look down here, here's an example of a low frequency, medium frequency, and high frequency wave. Okay, you can see the higher the frequency, the more waves pass a point per second. But if you have more waves passing a point per second, that also means that the waves are closer together. Therefore, the higher the frequency, the lower the wavelength. Okay, so higher frequency corresponds to lower wavelength. They are inversely related to each other. Okay, wavelength and frequency are inversely related to each other. Okay, so higher frequency, lower wavelength. Lower frequency means higher wavelength. Okay, so we have lambda for wavelength, that's typically measured in meters. We have frequency, that's the number of waves passing a point per second, that's measured in hertz. And then in the next video, we'll talk about doing calculations with these and do some more examples. Okay, so I'm going to stop it here, and then check out the next video. Please let me know if you have any questions.